Okay, so welcome everyone to this next ArtoCon 2025 talk. Today we're going to talk about Chameleon, a polymorphic engine based on R2. So, who am I? Well, I'm Bernat, or Gum3t as you prefer. I'm a security researcher and I like exploring and low-level stuff. But let's jump into the interesting stuff. What's Chameleon? Chameleon is a polymorphic engine for x86-64 position-independent shellcode. This kind of shellcode is the one that executes correctly regardless of its absolute load address, and we'll see why that's important later. So, what are the requirements of Chameleon? What were the requirements we set at the beginning for Chameleon? We wanted to evade or avoid signature-based detections in rent engagements. That's because we had a really good implant which is kind of hard to detect based on its behavior. So we wanted to improve the way it can avoid signature-based detection. So that's why I started creating Chameleon. And then we also don't want to break the given shellcode that we want to polymorph, which is kind of an obvious statement, but it was really hard to at the beginning of the process. So let's continue. This is the overall architecture or the architecture overview of Chameleon. We just get an original position-independent shellcode, we disassemble it, and then we apply certain mutations to this shellcode. These mutations may use a feature that generates pseudo-random shellcode that is also injected within the mutations. And then from it we generate a valid assembly code that we later assemble and get another version of the position-independent shellcode, which still works as intended, but it's completely different from the first one. Okay. So how do we disassemble, or what's the disassembly process of Chameleon? Well, to understand why we do what we do, we first have to look at on the problems that we have. And in x86-64, instructions have different sizes, which is kind of a mess, because each time you want to change some instructions for other ones, you have to patch all the jump or all the control flow instructions so they point to the correct address, and that's kind of difficult. And then we also can't use linear parsing for disassembly because it doesn't work, and we'll see now why. If we use linear parsing for disassembly, we'll find problems like the following. Given this sequence of bytes, we can see that if we disassemble using linear parsing, we get two different instructions. We get an add instruction and a jump instruction. But if you look closely, you'll see this jump instruction jumps in the middle of the add instruction. But if we trust this disassembly data and we use these assembly instructions and mutate them, we will lose some stuff and it will cause some corruptions in the shellcode. Well, not exactly corruptions, but problems that will break the control flow. And here we will see why. In this case, you can see the add instruction that we saw before and the jump instruction. But as you can see, there's an embedded increase instruction within the add instruction. So if we had trusted this, the other data, we would have lost this increase instruction. So we would have lost information. The solution, well, get the disassembly data from basic block graph or a control flow graph. And well, for more information, basic block is a straight line sequence of instructions with no branches except for the entry and no branches except from the exit. So it's a continuous block of instructions that runs smoothly. And how do we do it? Well, with R2, of course, we can use the AGF command to get the basic block graph of a function, and in this case we use it in Python with R2 pipe. We just get the original shellcode, we analyze the shellcode, then we list all the function offsets with AEF LQ, and later we just retrieve the basic block graph information in JSON format for each function offset. Here you can see the both functions. Where, here we retrieve the function offsets, and here we retrieve the JSON data for the control flow graph. We have to say that this data is later parsed into Python classes, so it's much easier to use for the mutations later. Okay, so how do we turn this parsed data into valid assembly code? Well, at the beginning, when we pass this data, we assign each block a label. So each block begins with its own label, and it's easy to, or we can use this label to identify the block and to jump to this block whenever we need it. And then we just parse all the control flow instructions, and we replace all the immediates with their correspondent label. And this is possible because on how basic block works. So each destination of a jump will always be the beginning of a new basic block. So we will always have the label corresponding to the immediate where the jump or the instruction is trying to go. Okay, so later these instructions may be the other instructions may be mutated or hard-coded into the assembly file that we are creating, and well, and a final jump is enforced at the end of each basic block to the following one, but we'll see later how, why is that, why do we do that, and why is it important. Okay, so let's talk about shellcode mutations. How do we mutate a shellcode, and how do we do it? So for this part, I want you to understand what mutation pattern pools are in this project. Each mutation pattern pool focuses on the mutation of an action. In this case, we can use the example of moving a value from register B to register A. So each mutation pattern pool has a set of match rules, and each match rule focuses on the detection of a pattern an action can have. For example, in this case, where we want to move a value from register B to register A, it can be done through a move, but it can also be done by pushing the source register and popping up to the destination register. But you can also use an exchange instruction. There are a lot of ways you can do it. Well, here the important part is that any match rule detects each kind of these patterns and returns the index where this pattern is found within a basic block. Then we have the mutation probability. This is the probability to apply a mutation once a pattern is found, and in this case it's a percentage. So we only want that 80% of these actions are mutated. So once a pattern is found, we apply the probability, and then based on the probability we decide if we apply the mutation or we don't. And finally, the generators. The generators focus on the generation of code equivalent to the found patterns. In this case, we may want to create a generator that uses a move, or a push and a pop, or an exchange, or some push, then we generate some random semantically neutral code, and then a pop, so it's like it's more hidden, the change of the value, and well, and it doesn't matter of the size, because at the end we are just treating with assembly code and labels, so we can just swap it out and we won't have any problem here. So we can create equivalent code as big as we want. And why is that important? Because at the end, this is done to allow you to create your own mutations, so you can create your own matching rules and your own generators, and you can detect patterns by opcodes, by bytes, by ISIL, and you also can generate your equivalent code. And I think this is very important because it allows you to create a lot of mutations without having to care about control flow within an x86 64-bit shellcode. And also I wanted to say here that it's not only limited to simple mutations, but you can also add or inject opaque predicates or some kind of routines that you're interested into injecting to your shellcode to obfuscate it. So let's keep going. Do you remember the enforced jump we had at the end of each basic block? Well, this now allows us to shuffle all of the basic blocks without breaking the control flow. As you can see here, at the end of each basic block, when we were disassembling it, we added a jump instruction through the next one. So, and this now allows us to shuffle all the basic blocks except from the first one, so the code is the control flow is not going to break. Of course, after shuffling all the blocks, we can always check for if there are still some blocks that are continuous, so we can just erase redundant jump instructions that would just jump to the next instruction. So this way we can avoid weird jumps. Okay, so as you saw before, or as you heard before, some generators can make use of a code generation feature. So what is it and how does it work? Well, this code generation feature is capable of creating semantically neutral shellcode blobs that can even include nested branches and loops. Semantically neutral code is code that changes the program appearance but not its behavior. Okay, so we have a general pool of registers that just has all the registers from RAX to RDX, RSI, RDI, and R8 to R15. And here we get a primary register. We choose one based on weights that are defined on the code. Then we check if it's the first time that we're using this register in the shellcode we are generating. So we check if it has been previously stored. If it hasn't been, then we create a storing. Well, we select a storing gadget and we select also a restoring gadget. Then we add the storing gadget into the shellcode we are generating, and we keep the restoring gadget apart to just know the size we need to take into account. Once we have the primary register, once we have chosen a primary register, we choose a secondary register from the stored registers. This way we don't have to check or to validate that this hasn't, we don't have to store it again. And once we have both registers, we select an instruction or a gadget, which all instructions or gadgets are defined also and have their own weights. And then we get compatible register sizes for the instruction of gadget that has been selected. For example, if we get a move RSP to some register, we have to make sure that this register is 64-bit, because we cannot move RSP value into AX, for example. So we then just choose the sizes of the register according to the instruction or the gadget capabilities. And then we finally generate and assemble the instruction or the gadget that was chosen. Finally, we check if there's still remaining space, and if there's still remaining space, we just loop again and again and again and again until we have no more space to keep generating instructions, because we only have space to add the restoring gadgets that we kept from the beginning. So we add the restoring gadgets and return the generated shellcode. And here you have some examples of these implementations. Here you have the example I gave you before, from that it's to move RSP to a certain register, and here we just specify that this kind of instruction only supports 64-bit register sizes, and this last value is the weight of the instruction. There are some instructional gadgets that are more complex. Here you can see a gadget that checks, well, that compares two registers and jumps according to some result. In this case, I won't go into the implementation, but you can see that there's some function here that's called get and junk instructions. Well, that's the function that gives this the code generation feature a lot of interesting stuff, because it allows to repeat in a loop the 4, 5, and 6 points from this loop. So you can inject here some other instructions or some more gadgets selected from the global gadget pool. So here you can manage to get embedded conditionals or embedded loops into this gadget. So this allows to create more complex shellcode and more real-looking shellcode. Okay, so after all this stuff, the generated shellcode is later hard-coded into the assembly that we are creating using DB. And finally, we just have to assemble the generated, well, or the created assembly. And here we are just using NASM, but we are working with Pancake to change it to RASM2. So if it's possible, it's going to be available in a few days. And well, I think now we have some time to go into the demos. And here you can see just creating generating a reverse TCP shell from Metasploit. And now we're going to polymorph it. And then here we're going to see the changes of the entry point. We will compare the changes of the entry point. I'll skip here a little bit. I'm extracting some data to create some images. And here you can see the basic pod graph before the polymorphing process. And here you can see the one after the polymorphic process. As you can see, it is very different, and it only has, in this case, it only has a couple mutations implemented, and it's also using the code generation feature. Okay, and here you will see it used in a more complex implant. In this case, the implant I was talking to you before. Here we are going to polymorph the implant. As you can see, we have both versions here, and now we're going to see how it still works without any kind of problem. Here it is. So that should be the same file. Here you are. And then we're going to get an exe file from this shellcode. So it's compiling now. And now we're going to execute it, and you'll see how it still works and retrieves the DNS records. So that should be all. And well, if you have any questions, I'll try to answer in the chat, and you can check the repo here. So feel free to check it and ask whatever you want. And well, thank you for being here, and enjoy R2Con.